Hey 12th graders, so we are starting our next unit, which is further differential calculus. And what that means is that we're still just talking about this brand new concept that we learned in our last unit. So we learned about this thing called derivatives. And we started out last unit with saying, okay, we have this thing called the tangent line. This tangent line just barely touches the curve at one point, this very important point where this line touches the curve. And we have a slope at that point, which really is represented by the slope of the tangent line, but the idea of the slope at that one point. And it's not always the same. The slope changes with some figure. As long as it's not a line, the slope will change. And so we said, okay, well, what if we wanted to know the slope at any point? And that is the derivative. The slope of the tangent line, or in other words, the slope at any point on a curve is the derivative. And so since it's not the same, it will be a function as opposed to just a number. So we're just expanding on that in this unit. We're going a little bit further, but really not that much further. We're just going to see all the different ways that we can look at it, and really we're just trying to increase our instincts with this, because our last unit is then going to go backwards through all of this. If we did deriving, if we derived or found the derivative, going backwards would be finding the integral, like multiplication and division undo each other. It's that sort of idea. So we just really want to make sure we feel comfortable with the idea of derivatives, and that's what this unit is about. We do a few more new things, but not that much. The goal of today, and especially with these first few problems, is that we want to use our derivatives as much as possible with easy problems in order to really understand what that relationship is, again, even more so. So a lot of you, I think, are going to be asking yourselves in this process, can't we just figure this out by looking at the original function? Yes. But when we get to the actual problems, the real problems that we're trying to do, the problems that we are getting to eventually, you won't be. And so you need to know how to use the derivative to answer this idea in order to then, when you have the harder problems show up, to be like, oh, well, if I just use the derivative, which my calculator can give me, or which I can find on my own, then I can use the derivative to answer this question. So when you find yourself saying, can't I just look at the original function and figure this out that way? Yes, but it's a story. It's a journey. Learn with me, build your instincts, and we'll get there. Okay, so sign diagrams. Sign diagrams are a way that we find maxima and minima. First derivative test means, hey, you take the derivative in order to find these guys, which makes sense because we know that with these maxima and minima, we call them local. This is a local maximum, maximum singular, maxima plural. This is a local minimum. And we know that this occurs when your derivative, your local maximum and your local minimum occur when your derivative f prime of x is equal to what number? We know that you have a maximum or a minimum when your derivative is equal to what number? Remember that since your derivative is the slope of your tangent line, and at a maximum or at a minimum, your tangent line is horizontal, which has a slope of 0, that means that your derivative is equal to 0, right? Anytime you hear about maximum or minimum, they're saying first, derivative, and second, is equal to 0. So here's a few things we already know. We also know that when your original function is increasing, that the derivative is then, it's a prime there, greater than 0, right? It's positive because the original function is increasing. as your original function is decreasing, we know that your derivative is less than 0. And again, increasing here, the derivative is greater than 0. So, taking all of this and turning it into a sign diagram. A sign diagram is pretty much, it's a number line, first of all. It's a number line that goes horizontal. Specifically, it's the number line that is your x-axis. So remember that your x-axis stays consistent between your regular and your derivatives, right? The only thing that changes in regards to what your labeling of your axes are is always x. Then sometimes it's f of x, or your y value, on the y-axis, or sometimes it's f prime of x. But x still always stays x. All of these are still functions of x. It never changes to a function of something else. So making a number line dealing with x in regards to original versus derivative makes sense, because that's the only thing that stays consistent when we're talking about one or the other. Okay, so we know that local maximums and local minimums, or just maximums and minimums, maxima and minima, occur when your derivative is equal to 0. So we have these numbers. I'm going to call it x sub 1 and x sub 2, because they're x numbers, numbers that go with x, and they're 2, 3, or 1 different numbers. It doesn't have to be 2. It could be 1 or 2. In this case, 2, because we have a maximum and a minimum. And these values are when the original function is at the maximum, and that same idea when f prime of x crosses the x-axis. In other words, it's the x-intercepts of your derivative, okay? So that connection, that these values are the x values when your original function is at a maximum or minimum, or, in other words, when they cross the x-axis, when they have an x-intercept. So for this guy, your derivative is going down in the middle, which means that your derivative is negative. Versus when your original is going up, your derivative is positive. This is a sign diagram. It kind of boils everything down to just this little symbol here. And they can be really, really quick to make, and they can increase your instinct with a problem as long as you understand how to use them. So at first we're going to have to kind of learn how to use them, kind of learn how to make them, and then once we get super comfortable with it, it can be a great tool to use, and is often a tool used when we're talking about calculus. Once we make the derivative sign diagram, we can then determine which one is our maximum and which one is our minimum by just looking at these symbols. When it's a positive, and then a negative, that means first you increased and then you decreased, which means that x sub 1 is your what? It's your maximum, right? So when it first is positive and then it's negative, it means, hey, first we increased and then we decreased, so you created this maximum. And then, on the other hand, if you have on either side a negative and then a positive, it means first you decreased and then you increased, which means you created a minimum. So looking at that behavior around a sign diagram, I first was increasing. You could even do this, increase and then decrease, right? Increase, decrease. And you're like, oh, that's a maximum, versus decrease and then increase, that would make a minimum, okay? Just thought processes here, all right? So we're gonna use this for our following functions. Yes, you can absolutely figure out where the maximum and the minimum are from this without using your derivative. However, we need to get familiar with this instinct and familiar with this process, so that way when it gets harder and we can't just figure it out right away, we have a process that's quick and easy and we know how to use it.